Okay, welcome back to the CMT Journal Club. We have Anton Kapustin from Caltech. He's also here giving the morning talk. Tell us about anomalies and spin chains. Thanks for coming. Thanks for being here.
Thank you for having me here. I've been talking with UCLA for a while. Maybe never. Spoke with IPAM. This is I'm going to talk about some work we're still in progress with Nikita, who's now a postdoc at IS, my student at Caltech. So anomalies is kind of old subject, which originated in quantum field theory. So I'll begin with talking about anomalies in quantum field theory, and then, the talk is not about that, but as a motivation. Because, and then I'll explain why Lipschultz Matters theorem, for mechanics, is actually seems like it should have some with anomalies, and lots of people observe this, but I think it does not make it very precise. And one of my goals is to explain how to make it precise, and provide some general statement which involves Lipschultz Matters as a special case. And the way I'm going to do it is by upgrading a little bit, generalizing a little bit of work of Nayak and else about anomalies of non-on-site symmetries on the lattice. So they discussed the general case. I'm just going to stick with one-dimensional case, and then I remind how that works according to Nayak and else, and then I explain what the generalizations are. I'm not going to try to give precise definitions because it'll take too long, but it's the informal version. And finally, if time permits, I'll finally define at least something which I want to mention. I'll define it. So the goal is to get something rigorous understanding of what it means to have an anomaly on the lattice. But first, something very non-rigorous, namely quantum field theory. So quantum field theory is notoriously subject difficult to understand, define, but all intuition comes from, about anomalies comes from there. So what is it? Well, we have some quantum field theory with a global symmetry called G always, and you can ask, can you gauge it? That's the first thing, which is not very clear what it means. But informally, physicists know what it means to gauge a symmetry. Roughly speaking, coupled to background gauge field, more advanced, and consider your space-time equipped with some bundle, G bundle, and connection with this G bundle. You want to couple the theory to this data, bundle with the connection in a consistent way. So even if you suppose don't succeed, then you say you have an anomaly. Or more precisely, a truth anomaly. So why is it called a truth anomaly? Well, actually, he didn't invent them. I think it was Wes and Zumino who essentially invented the truth anomalies. But what he observed is that if they're non-zero, then they provide constraints on the inferred behavior of quantum field theories. That is known, as a truth anomaly match. So Sut argued non-rigorously again that anomalies don't change under normalization group. So if you know an anomaly of the theory at short distances, but know nothing about the long distance behavior, then you know at least that the long distance behavior, if it's effective field theory, must have exactly the same anomaly. So in particular, one corollary is that if you have a non-zero anomaly, then you cannot have a trivially gapped symmetric vacuum. So because it would have trivial theory. So by the way, I got a lot of term of anomaly, I think got a lot of criticism for it actually. I started using it because people use a truth anomaly matching. Would stress differently, truth anomaly matching. We can talk about truth anomaly. So an anti-cyber for years he would just tell me this is wrong, you shouldn't call it truth anomaly, but then eventually give up because some should be a term for this, some obstruction to gauging. But, why not call it truth anomaly? So there are two questions about this. I was going to ask, first of all, actually, where do they take value? So what is in computing anomaly? Where does it take value? And second, how to compute it? The second question I'm not going to address at all because I'm not going to actually reach some quantum field theory. And it's subtle and non-trivial because quantum field theory is subtle. But at least we can try to answer where they take values. So first of all, these are some usual answers. Originally, people thought about Lie groups, or precisely connected Lie groups, like SU2 or U1 or something like that. And they said, became already in the early in the 70s, that anomalies, and we want correspondence with Chern-Simons terms for G gauge field in one dimension higher. But here in this talk, D is always going to be a spatial dimension, a little d. So it's a quantum field theory, little d spatial dimension, one-time dimensions. We're going to figure out where anomalies take values. Just try to classify possible Chern-Simons terms in one dimension higher. Well, more recently, people started asking about anomalies for finite groups. For finite groups, it was proposed that they take values of group cohomology. I'll remind you later what cohomology is, but it's some group, abelian group, and compute if you know the group for any dimension. And originally, it was observed in the context, I think, of string theory. People talk about orbital folding, conformal filtering. Well, there's no abstractions in general. In that case, D was 1, because it's 1 plus 1 dimensional safety, so it's greater than H3. Now, more recently, people realized, well, there's actually not quite a complete answer. We're going to talk about not group cohomology, but one-dimensional representations of the oriented bordism group. Of what? Of the classifying space of this group. So there is some for any group G, there exists some space called classifying space of G bundles. And for finite G, there's an easier description. It is any topological space such that it's pi 1 is G, and all other homomorphic groups are trivial. So this has one group, one of the group. Now, of course, there are lots of such spaces, but for this purposes, it's only important to know it's the homotopy type of the space, because once you know its homotopy type, its bordism is well defined. So then you take it's an abelian group. This thing. They just take one-dimensional representation of this group. And that's your answer, which is a better answer than that. And there's a way to, it's for unitary symmetries. I'm going to talk about only unitary and bosonic ones, but the principle can incorporate time reversal symmetries and permanence. Anyway, so let's look at low dimensions. First of all, why this bordism? What's the advantage? Well, it's supposed to take into account mixed anomalies. The anomaly which involve sort of mix between gravity and G. So when you gauge G, you can get some abstraction. When you try to put the system on a curved manifold, quantum field theory, you get abstraction to that too. So you cannot ensure invariance under diffeomorphisms, so gravitational anomaly, but they can also be mixed ones. And that's what supposedly what this guy captures. But the low dimensions, which are going to stay, it doesn't even matter, because one can show that there's no difference. First of all, this group is actually the same as singular cohomology of the classifying space of G. And I just say singular cohomology is usual, BG is a topological space. That's ordinary homology and cohomology. And we just call it singular cohomology because for whatever reasons, it's standard name for it. It's really just usual topological thing. So in bordism and homologies are the same for low dimensions. So it's dual happens to be, it's basically just a singular cohomology, the topological homology of the space with U1 conditions. And finally, in this dimension, well, in all dimensions, but for finite G, we equate the topological cohomology of this mysterious classifying space and group cohomology of the group itself. In the end, you get the same answer, so it doesn't matter. You can just forget about this bordism stuff. All dimensions. There are no mixed anomalies, in other words. Gravity is apart. Internal symmetry and quantum field theory. Unless you have like time reversal. Anyway, to summarize, what QFT tells us in bosonic anomalies in quantum field theory takes values in this either group cohomology or singular cohomology of the classifying space with U1 conditions. And 4 equals 1 in H3. The group cohomology or usual topological cohomology of the classifying space. There are no mixed anomalies. Okay, so what is this cohomology and why does it describe anything at all? So just well, it's easy to understand in dimension 0, it equals 0. So that is in quantum mechanics, because it's of equals 0 quantum field theory is. So I said that anomalies are structured to gauging. Let's try to understand why this guy, why obstructions to gauging take values here. Well, first of all, what exactly this group is? Well, it's a group of two cocycles modular two coboundaries. What does it mean? Well, first of all, cocycle. What's a cocycle in a group? Well, a two cocycle is a simple thing. It's a function of pair of elements with values in U1 because it's homology with coefficients in U1. Could be some other abelian group. And it satisfies the following cocycle condition. So that's the condition. And then coboundary is some special solution of this equation, namely solution of this form, where psi is a function of a single element. So some strange definition, the first side. Now, so you can check, of course, that this any solution of any function of these two arguments of this form solves this. Also, in general, we can define cohomology with coefficients in any abelian group. And usually, well, here I use this multiplication because I think about U1 as a group of complex numbers with absolute value 1, and then the group operation multiplication with complex numbers. But the most standard to say the group operation is addition, so then it would sort of multiplication by plus. So why is it related to anomalies? Well, first of all, where do they arise naturally? Well, of course, two cocycles arise from projective representations of this group. So in normal representation is a sum of a group which is on some Hilbert space H, some unitary, one for every group element, which satisfy this condition but without the row. And when you do have this additional phase, say it's dealing with projective representation, sometimes the twisted homomorphisms from the group of unitaries. One can also say, well, it's an ordinary homomorphism if you forget about the U1 phase. But then you need to quotient your group of unitary operators by the subgroup of identity times unit times a phase. That's called U1, so that's called usually projective unitary group of the Hilbert space. So that's the name, why the name projective representation. In the old literature, the people call it array representation, because a vector in the Hilbert space after scalar factor of absolute value 1 is called array. So that is okay. So what does it mean to have non-zero anomaly? Well, suppose you have this non-trivial. Okay, the freedom of redefining this. Well, of course, you can try to kill this row by redefining what u hat of G is by multiplying by some scalar factor with absolute value 1. But if you cannot say if the row is non-trivial, it's not a coboundary. There's no way to get rid of this row. Suppose it's non-trivial. What this means that there's no G-invariant ray in the whole Hilbert space. So, and what does it mean? What are the physical consequences? Well, first of all, we try to gauge. Well, what does it mean to gauge? Well, you need to look at all invariant rays, right? But there are no invariant rays. So your Hilbert space is going to be, after gauging, going to be zero dimensional. The only thing that you allow is zero vector. So basically, there's nowhere to be. It's one consequence, and that's in agreement with this. The fact that the anomaly is supposed to have structure to gauging. Also, even if you don't gauge, there's a consequence. If you look at ground states of any G-invariant Hamiltonian on this Hilbert space, well, of course, they form representation, which you can decompose into reducibles if you want, but there's no reducible representation of dimensional 1. So any all ground states will be degenerate. That's another sort of dynamical consequence of this projectiveness. Just for future use, let's look at the degree 3 cohomology. That's going to write definitions. So I have a 3 cocycle model 3 coboundary. The 3 cocycle is now a function of 3 arguments with now a 5-term equation. So modular cocycle, modular coboundaries, which are solutions of this equation, which are this form, where psi is an arbitrary function of 2 arguments. So there's some nice way to memorize this equation. I'm going to get into. if you can remember it.
So can I ask a question before the previous slide? So when you said that so is this the statement about there is no G invariant ray? Is that a statement about like, sorry, is that a statement about the particular element in H2, or is that a statement?
Suppose you have non-zero element on H2, so your representation is really projective, not just some fake projective. Then we can you can remove this phase,
right,
by just redefining this. You had it's not a real projective. So, I mean, usually people say, well, when you gauge, you want to restrict to invariant vectors, right? But I think it's better to say invariant rays because anyway, the overall phase. Who cares about the overall phase? You want the projector to this subspace to be invariant on the space itself. So that's. We'll say, if you can, of course, if you have invariant rays, then you can also say you have choose invariant vectors by redefining what even by you have this phase.
It's saying invariant array is a 1D representation, but none of those are projected. Sorry, just.
So that's a horrible formula, but okay, just keep it in mind. So basically, 3K cycle is a if you want a function of 3 elements of the group. Now there's something which is a technical issue here, kind of important technical issue, because in physics, finite groups are really not what we like the best. We like Lie group. Well, finite groups can think of it as Lie groups, which are 0-dimensional. But okay, when you go into more interesting Lie groups, then life is a bit more complicated. So, for example, okay, what do we expect first of all? So these answers, I mean, like, remember I told you where anomalies take values for finite groups, and it has a separate answer for Lie groups. They didn't seem to obviously be the same. So, okay, so what's the difference? Well, why is it important, this distinction? Well, for example, let's look at the U1 scenario, parallel edge of a interconopole system. In that case, we expect anomalies to take values in integers. The anomalies for what? Well, for the quantum field theory on the boundary, on the edge. Why will see there like Hall conductance by this boundary correspondent, which I want to mention again. We expect that the topological invariant of the bulk is reflected in the anomaly of the quantum field theory on the boundary, and never gap it out. So that is an integer, then in the bulk we expect integer in the anomalies. Or we say the level of this U1 current algebra, it's conformal field theory on the edge. Well, it does have to. Okay, so we expect that. If you forget about this answer, which I give separate answer for Lie groups, if you just naively generalize and try to generalize the answer for finite groups, you say, well, that's where we expect the anomalies. This group though is trivial because BU1 is actually very simple. You can take it just to be infinite dimensional projective space, and that's a very simple space. All its odd dimensional homology just vanishes. So for all n, particular form equals 1 it vanishes. So the dual also vanishes. Actually, for C2, same thing happens. Okay, it's more complicated there, but still true that H3 vanishes. And again, we expect anomaly to be integers because it's an abelian sort of Hall conductance. Okay, so now of course, quantum field theory, people originally said, well, it's Chern-Simons terms. Here we can use Chern-Simons prescription to get the right answer, but what do we do in the case where Lie group, which is a Lie group, but not connected like this one? So it's a mixture of sort of a finite and the U1, right? So it's nice to have a general answer. Now, like what went wrong? Well, for a finite group, there are 2 different ways to look at the same prescription, right? You can either say you have a group of homology, you can do topological homology of some classifying space. Now, but it doesn't. Actually for Lie groups is a different things. I basically said, okay, let's try this one, and it didn't work. Right? Now we can try to try this thing. Maybe it works better. Maybe that's the right generalization. Well, first of all, we win by cocycle in the group. It's a Lie group. Well, it's a Lie group, in particular, topological groups, it's continuous cocycles. Well, it doesn't work because, for example, for SO3, there are no continuous 2 cocycles. And then never there's a projective representation for this group. So that's even doesn't really, for 0 dimension, it doesn't make sense to work. So use arbitrary cycles and know that actually there's no way to compute this thing. It just nobody knows what. Maybe somebody can compute it, but nobody ever did. Even though in degree 2, in degree 3, like literally nothing is known. Why is that? Because it's insanity to consider arbitrary functions, no constraints on continuity or anything. Arbitrary functions, say on a circle. What is that? So, or some Lie group. And you're supposed to take these solutions in some horrible, arbitrary, completely discontinuous solutions, and then factor over some equally ridiculous subset. Nobody knows what you're going to get. So basically, arbitrary function on an uncountably infinite set is just insanity. So it's not like this definition doesn't make sense, just extremely useless. So now, Chen, Wu, and Wen proposed to use measurable cycles. Well, measurable is not much better. Measurable functions can be pretty wild too. So there's zero physical explanation of why they're relevant. If you're going to have a functional Lie group, you want to have like slot function. It's a manifold of Lie group. We'll see later how it's resolved. So anyway, so let's finally let's leave on a field theory. There's a lot more for motivation, but one of the motivations that we should understand better the case of Lie groups. We don't really fully understand how to, or even where the anomaly takes values. Anyway, let's look at Lifshultz Matters theorem. Very reminiscent of this Truth anomaly matching. It says, well, it's a more specific thing. Originally, just a statement about 1D spin chain, which has translational symmetry and on-site SO3 symmetry. So if the on-site Hilbert space is a projective representation of SO3, then the ground state and the thermodynamic limit cannot be unique, gap, and completely invariant of both symmetries, translation with SO3. So that's the original statement. And there was, of course, lots of generalizations, in particular, mathematically rigorous work by Ogata and Tasaki, and Ogata, more recent one by Ogata, Tachikawa, Tasaki, which, for example, proves a version of this for arbitrary finite symmetry group. And then extract something also for Lie groups, but in some very, for someone not for some ugly way. Simple statement. If you have a projective representation, then you must break the translational symmetry or some for your group or your on-site group. Now, clearly, it's very similar, and many authors suggested that LSM theorem and its generalizations are a manifestation for QFT anomaly. It's a bit confusing, but not clear which anomaly we're talking about. So now, since it's now important to have both translations and SO3, first thought, well, it's a mixed anomaly between translations and SO3. And quantum field theory, there are no such anomalies because there's just nothing than diffeomorphisms of any kind in screen one dimension. So that's not the right interpretation. Now, there's an example here, the 21. So, they propose that a field theory has some sort of eminent, they call it Z2 symmetry, or descends from translational symmetry on the lattice. And what's the anomaly, according to LSM, in QFT, just a mixed number between SO3 and this Z2. That's a perfectly fine interpretation, but except, as I already said, when you have like a Lie group which is not, in general, when you have a Lie group which is not connected like this one, how do you classify what anomaly is? I'm not sure how to say the generality. Also, well, that assumes that effective field theory has this Z2 symmetry, but nobody said it should have. So the claim is basically that if it does, then there should be some anomaly there to match its LSM. But what if it doesn't? It doesn't have to be there. And push that, we want to have some interpretation which doesn't rely on quantum field theory at all, ideally, because it's none of it is going to be rigorous. And we want to have precise definition. And let's just try to stay within lattice systems and just formulate, try to find some general statement about anomalies of lattice systems from which LSM will follow. And there's a paper also by Seif Nashri, which addresses a similar question, but his methods are different. Okay, so now Actually, this approach was also taken a long time ago by Nayak and else. And their problem was they used anomalies specifically as they started with SPT phases. And they proposed that anomalies of the lattice systems in the dimensions are what are a way to classify SPT phases in one dimension higher. So they looked again also at unitary symmetries. They thought about the bulk, which is D+1 dimensional, and on-site symmetries in the bulk. But they proposed that if you look at the edge of the system, then which is symmetric, then the edge also, of course, is acted upon by the same group. But this action need not be completely local, it need not be on-site. This is what the interpretation was. Okay, so basically it's local, but not on-site. I'll explain specifically what they assume by local, but they assume that it's local, but not on-site, and argued that the anomalies are labeled by this group, by the group homology. And then, right, so in the proposal, this is actually the way to classify SPTs, so explaining the results. Now, here are important things. First of all, they assume that the edge is a lattice systems, not the quantum field theory. It's not obvious at all. So nobody said that the edge of a SPT should be thought as lattice systems. Because all degrees of freedom there, but who said they're not naturally latticized. Also, they assume that the action of the G on this edge lattice is by unitary circuits. I'll explain later what this means. That's what it means to be, what the said action is local, that's what I mean. They meant that it's acted by circuits. It's again, probably not very obvious. It's an assumption. Now, on the plus side, the definition for one dimension, at least, is mathematically rigorous and purely kinematic. They say, well, as soon as you specify this local but non-on-site action of a symmetry on a 1D system, we can actually define a mathematical procedure for extracting a class in H3 degree 3 cohomology. And you don't need to know Hamiltonian or anything, just purely kinematically of the action of a symmetry on a lattice. And actually, with even clear what it obstructs, like the way it defines clear what the meaning of obstruction is. A very nice approach. We would like to proceed, but let me also say also they also show within this setup that there's something similar to LSM theorem. So if a G acts by circuits on a one dimension, and there is a Hamiltonian, which is grounded as G invariant and short range entangled, then the anomaly must vanish. And I put it the converse statement that if the anomaly is non-zero, no G invariant Hamiltonian can have a G invariant and short range entangled ground state. So that's very similar to LSM. But it's a distinct result because LSM is about symmetry, which involves translations and some on-site symmetry. And translations are not sort of, to explain what circuit is on the next slides, but from a circuit. So it's not local in the same sense as and I think also assume. It's not a spec. I cannot deduce LSM from this result. Plus another difference. I forgot to put it here on the slide. Another difference is actually LSM is about something about ruling out gapped gapped symmetric states. Here they're ruling out gapped Froehlich entangles. Sorry, invariant in Froehlich entangled states. Now it's a bit different. In one dimension, everybody believes that all gapped states actually Froehlich entangled, but nobody ever proved that. That's part of the problem. Well, maybe not so hard, but there's nobody ever proved. So strictly speaking, LSM is stronger in some sense because you could imagine maybe by some miracle there are some states which are gapped, not Froehlich entangled even in one dimension. Then this sort of not say anything about LSM does.
Well, doesn't Hastings' theorem,
Okay.
Hastings' theorem, like the fact that you have a gap system in 1D, doesn't that?
Is it also not what people say that it doesn't prove aerial law for them?
Yeah.
But by itself is not strong enough to prove that all gapped are Froehlich and all. There's some results about approximating by matrix product states, but also doesn't imply that they are actually equivalent to matrix product states. This is not established. Well, luckily, I don't know, maybe it's not very hard to prove it, but in all cases I know that's not a real obstacle, you know. There's also hastings and so on, actually typically enough to establish everything just for gap states. You don't need to know that all gaps. Anyway, so another defect is that it's kind of useless if G is not a finite group, because saying that some class obstructs existence of symmetric state is useless if you cannot even compute this class and decide whether it's zero, non-zero. As I already said, if you allow arbitrary cocycles on a Lie group, like if somebody writes down this horrible function, how do you decide if it's a co-boundary or not? There's no efficient way. This is distinctly unmanageable. So we need something better for Lie groups. Okay, so now let me explain in more detail what Nayak and Delsa mean by local symmetry, local acting symmetry. So first of all, what's the system? The system is have an on-set Hilbert space, which I assume to be finite dimensional, so it's a kind of skin chain. You have an algebra local observable, which is an infinite product like this. Each term is just each factor is the matrix algebra. Because bounded operators mean, well, finite vector space just means that the matrices. Actually, each term is a C-star algebra with finite dimensional C-star algebra. To take a product, you get a star algebra, so the notion of a dagger, and has a norm because each of these guys has a form, usual, the largest eigenvalue. It's not a C-star algebra, but if you complete it with quasi-local observable, which I mentioned in the pre-talk, then you get some C-star algebra. It's a nice object. Now, what are symmetries? Well, symmetries are automorphisms either of this guy or the bigger quasi-local observable elements. In principle, symmetry can map a local observable to quasi-local ones, but not the ones you normally encounter in physics actually map a local to local, you know, like green tails. Anyway, so what is automorphism? The bijective linear map, which preserves the algebra structure, the star, plays nicely with the star. That's how what is an actual symmetry supposed to look like. Now, for locality, well, we need to first of all specify some additional notions. First of all, what's the notion of a unitary gate or simply a gate? It's a very simple automorphism where you just conjugate your all observables by some fixed unitary element in the local observables, so the gate. Math is usually known as add U, integration with U, adjoint action. Next, you have a notion of a block partitioned unitary or partitioned unitary. Is when you do so many gates at the same time, but their supports, like where they're non-trivial, are non-overlapping, but they don't need to worry whether they're commuting or not. It's called block partitioned unitary. So I denote simplistically, I denote the all unitary local observables with this UL. So each of these guys is just a unitary local observable, but they can have an infinite number of them. That's fine because, you know, if you're acting on a local observable, all these guys are going to cancel out basically. So only a finite number of them. So it's a well-defined automorphism. And also one typically assumes that they have a bounded diameter. So each of these guys lives on some subset of the lattice, and you assume that it's an infinite product, but they're assuming that the diameter of this guy is always bounded with some number. I don't think this number is a different unitary thing. But it's a bad notation, a bad terminology, because a unitary is a unitary element somewhere. It's not a unitary element anywhere. It's a collection of unitary elements. It's an infinite collection. Anyway, so just. And finally, a circuit is just composition of a finite number of these guys. Essentially, you want to form a group, and you just take the closure of this thing and the group operation. That's called a circuit, group of circuits. It's some nice summary. Okay, let me explain the Nayak-Elsa procedure. So, Nayak-Elsa procedure. So, we consider first of all, what's an action of a group? Well, you want to map. Sorry, it was the capital. It will be homomorphism from alpha to the group of circuits. So for every element of the group, you're going to have some alpha. Now, and there's a homomorphism, so alpha of GH is the same as alpha of G times alpha of H. Okay, now, next step, you split each of these automorphisms into a product. of two automorphisms. One x on the left, sort of, well, what I mean by left means x, let's say alpha plus, roughly x on the right half chains. But it means that x trivially on all local observables which are sufficiently far to the left. It can like overlap one, but it's definitely act trivial on something which is far to the left. And then, well, you could have, you know, you pick, say, like this guy. And once you pick it, then of course you can just take this as the inverse of that and find what this is. You demand you split in such a way that this alpha minus acted on some trivial on thing supported far to the right. So basically, you want to separate your action of the group into something which acts non-trivially only here and only there. So left and right half chains, so some overlaps. Now, you don't require them to each of these to form a homomorphism. But if you don't care about this, you can always do that. Not hard to show. But then they don't satisfy, well, they fail to satisfy homomorphism property only up to some defect which is local. Say alpha plus acts on the whole half chains, half infinite chain. But the failure to satisfy this homomorphism is only up to local operator by their conjugation by local observable. This is now a function of two group elements. And now here, some computation shows that this combination of these V's and alphas is actually identity of effect. It commutes with everything you can check. And since it commutes with everything, it must be a scalar thing. So it's just, and plus it's unitary. A unitary thing, which is a scalar, is just base. That's how you define your 3K cycle. Well, why is it 3K cycle? It's a function of 3 elements. You're supposed to check the cycle condition. Some pretty hairy computation shows that it is a sub-3K cycle. And a further hairy computation shows that all these choices you made, like how you split, for example, alpha into alpha plus and alpha minus, how you pick this V, which is not unique either. None of this changes the cohomology class of this cycle. It's not changed by coboundary. It's pretty hairy. Okay, so now I want to put LSM into this picture. So we talk about why not everything is a circuit. Well, there's a more general notion called quantum cellular automata.
Sorry, just one question. So that was on infinite systems, right?
Yeah, just problems on infinite systems.
No boundary and
no boundary.
And do these local things arise at the boundary? Typically?
These local things arise only when where you split. You should pick arbitrarily where you zero is enough on the chain.
So
they're going to live in the neighborhood of this guy. They'll some radius, finite radius.
Okay.
The point is basically once your circuit has a finite radius of the gates, this V lives on something which is like at most like twice that radius.
Yeah.
So
right.
This is why I say it's rigorous. Now there are more things which are physical but more general than circuits. Now, so what are they? Well, no, translations, not a circuit. What is it then? Well, it's still a nice thing. So first of all, it's a notion. Quantum cell automaton is an automorphism of these local observables, which maps any strictly local on some particular site to something which lives on an interval of length 2r about the site, sort of ball of diameter 2r that site. So you map local to local, but that cannot local to particular site, you have spread it by finite radius. So such an automorphism is called a QCA radius r. And now translation, for example, by 1 is clearly QCA radius 1. This is shift observable by one site. Now, they form a subgroup, which is not hard to show, of all automorphisms. Now, clearly, every circuit has a QCA. It's again clear from the components of the gates radius. But not all QCAs are circuits. And that's not a trivial theorem. So there is a paper by Gross, Nesme, Waltz, and Werner, which is pretty old by now, which says actually there's an abstraction. And they actually not just show the translation are not circuits. They actually completely solve the problem of which QCAs are circuits and which are. They say that, well, there's some number, it's not a number, there's some homomorphism from a group of QCAs to some other group, which is actually a abelian group, whose kernel is precisely circuits. So, and there's even a way to compute this index. I call it GenBW index. So where does it take values? Well, it's simple when all your v's, for example, are qubits. Then you just have a single integer, which labels this where the index values. But you have, like, say, if your v has dimension 6, then there are two prime numbers which participate, 2 and 3. So you have z times z. There's like a separate integer for each prime factor. So why is that? Well, you can imagine, say, for example, each v is a product of 2-dimensional space and 3-dimensional space. And you can move you can take a stacking of qubits and qubits. You can move qubits independent of qubits, right? So both translations are clearly, like, probably cannot really, if they're independent invariants, right? Each of them cannot be realized in different ways. So you need to have 2 integers. So, by the way, and I think it turns out if you have Hilbert space with dimension 4, you still have only 1 integer because it's power of 2. So that's why I prefer, like, you just look at all primes which occur, and all primes which divide this guy, and then just there's 1 z for each of these points. Now, finally, get to results. So I want to generalize this Nyack and Elsa procedure, and now I want to generalize it in different directions. First of all, I want to allow translations and more generally arbitrary quantum cell automata. But also I can do even more. I can generalize even further by saying, well, for example, with this procedure of factorizing things, so that I can also try to factorize in these 2 circuits, a pair of circuits. I say there's an abstraction. I'm doing it in the way that each of them is homomorphism. So now you could try to factorize in something with tails, something which looks like a circuit that has some tails. Now, well, if you do that, then it's natural to say that alpha maybe itself has a tail. So it's not like strictly, maybe it doesn't map local to local, maybe it maps local to quasi-local with some tails. So hence we like naturally led to notion of some locality preserving automorphism. I'll say later if I have time what it is, but some much larger group, which first of all it maps quasi-local to quasi-local, contains all quantum cell automata, but also more. For example, time evolutions with local Hamiltonians.
So is it true that it can be generated from time evolutions and something like translations?
Yeah, I'll actually mention. Yeah, I'll actually say it here. So now so here's the result, which says that if you have any homomorphism from your group to this locality preserving homomorphisms in this sense, which I'm going to let to make this later, that is basically any approximately local action of the group on your system, then we can define some element of H3 of the group, and this index. Now this has the following interpretation. But the point is that in general, alpha of some element can be some QCA or some general thing, which is not evolution. But turns out there's an important difficult result by these 3 guys, a very recent one, well, very recent. They showed actually this index is well defined not only for QCAs, but also for these more general locality preserving guys. Suppose it vanishes, then you have a simple interpretation of this anomaly index. If it vanishes, there's if the image of this alpha is in this guy with vanishing GMVW index, then our anomaly index is an abstraction again to writing this as a commuting homomorphisms, which check separately on the left and the right chain. When I say separately, I mean like separately for some tails. I mentioned that the guy is simply alpha plus, it acts mostly on the right, but also with some tail which decays to the left. It's almost identical to the left. Same for the alpha minus. It's one of our approximately localized. Why do we need to make this proviso? Well, because another result of this also GMVW is that if you have non-zero GMVW index, you don't need to compute anything. There's just no way to split the thing like this anyway. It's already abstraction. So if you want to interpret this guy as an abstraction, then you better assume that it's basically GMVW index is for one particular automorphism. And if it's non-trivial, there's no way to split it into left and right. But suppose it vanishes for all the automorphisms. It's still, if you look them taken together, it may still be an abstraction for splitting them consistently so that all of them form a homomorphism. So that's meaning of the anomaly index. Again, there's a further result, which includes both LSM and else special cases. Suppose I have this homomorphism, and suppose there is some Hamiltonian whose ground state is G-invariant and gap. Then the anomaly index vanishes. Again, which means that the anomaly index is not vanishing, then no G-invariant Hamiltonian can have a gap symmetric ground state. So that's improvement on Nayak and else because we allow translations here, and we also prove it for gap. You cannot have any gap state, not just short-range entangle state. So now, as I said, LSM follows from this. Let me explain how. That's the interesting part, I guess. Suppose you have a group with some on-site symmetry, but acts on each on-site space separately, but projective with some two-per cycle. Well, Z just acts by translations. That's LSM setup. Now, we can show using some simple topology that the H3 of the product group is with the sum of these two, H3 for the G0 and H2 of G0. Some simple algebraic topology. Now, the part of the index which is here has to vanish because G0 acts on site. So this part, on the other hand, is sort of a mixed anomaly between G0 and translations. So we want to compute the part which is here. The claim is actually precisely the class of this cocycle rho. So how do we see that actually it's rho? Well, just do Nayak and else with some slight twist. Okay, so let me be more precise. We have this projective representation. So the homomorphism from G0 to unitary groups for the on-site Hilbert space. And what does corresponding homomorphism looks like? Well, just conjugate with the product, infinite product. You know, each of these guys is completely observable on some site J, which depends on the on-site thing. We just conjugate with all infinity of this. That's well defined because the local observables, it doesn't even care about most of them. It's sweet spot from them. Okay, so now the problem is that you cannot directly apply Nayak and else because we have that plus translations, and those are not certains. Here's an easy way out. Let's stack with an identical spin chain on which G0 acts trivially, but translations act is just the same as it was before, except in the opposite direction. Now, I should mention that GNVW index is additive under composition, under stacking. So on a composite system, translations actually act with a zero index, and therefore, by this result of GNVW must be a certain. So let's see how it works exactly. Well, let's, for example, suppose how do you realize? So the blue one is the original system, the red one is the additional copy that we had. Well, you can consider first of all swap, it's clearly a circuit, and sort of a shifted swap like this. Now you can see that if you compose, first do this and then do that, precisely going to shift, say this guy going to be go like here, and by this like this, shift it to the right. While the red one, you're going to move down here and then move like so the position of these two guys is precisely it translates the lower copy to the right and the red copy to the left. So now, okay, so and we can also now we can restrict this in a normal way. You know how to restrict circuits. So we get so like this is automorphism. It's clear what this means. So say this guy. So he moves like this, and then it's here. Anyway, so it's a bit different, yeah. So it's different for well, it does something pretty complicated in general. But anyway, so this is the picture, and you can just that's how you restrict the translations, and it's for automorphisms of the G0, just just truncate them to the right. And then you compute this. Well, what is supposed to do? Well, this suppose you should see the failure of being a homomorphism. Well, if you act, say, with some group element and translation, you're supposed to do, then you act with just a simple group element of the on-site structure. You would expect maybe to get this if it was a homomorphism, where this is a translation, sort of half translation. but actually you don't get that they're equal, because homomorphism is only homomorphism after conjugation of something. And something turns out to be this, the usually observable, which prevents the transformation of G on the very first site, because the first site is different from others. So this guy now depends on a pair of group elements. The group element now is an element of G naught and translation. And I don't make special cases like no translation by one side to the right. In that case, that's what you get. If they're both just on-site symmetries, get just do one because these are anomaly free. Downside. Okay, and then you have to compute plug into the formula, and you discover that given the triple cycle rule. Now, another part of the work is how to generalize this to Lie group symmetries. Now, first of all, a Lie group is simultaneously a group and a smooth manifold. That's a problem, the difficulty. Now, on the other hand, when you consider a Lie group, you don't care about arbitrary homomorphism to say unitary groups of a Hilbert space. Nobody cares about those. You want to know which are smooth, right? So the Hilbert space, the unitary group itself has a topology. In fact, it's an infinite dimensional manifold. And we want the homomorphism to depend smoothly on the group element. So if you look at particular action of the group on site, it's clear what it meant by a smooth homomorphism. But here dealing with spin chains, we're supposed to look at smooth homomorphism from a group, our Lie group, into some of this infinite dimensional creature, either this group of quantum cell automata, or better, this maybe all kinds of automorphisms. Now, are these things manifolds? Does it make sense to say that something is smooth? Well, in general, no, probably. So from the but there is some subgroup of this guy, which I call almost a unitary, almost local automorphism. So UAL. It's pretty natural and kind of is like an infinite dimensional manifold. So it includes all the things which you care about, like smooth on-site, Lie group actions, translations, and time evolutions by finite range autonomies, and some other things. And in better news, so for Lie groups, actually there's a better version of group cohomology, which people know about. It takes into account that both G and U1 are smooth manifolds. Called differential group cohomology, like this. In fact, you can define arbitrary Lie group G and abelian Lie group A, doesn't be U1. And we show that actually you can assign to any smooth homomorphism, any smooth action of the group of your Lie group on your spin chain, you can get a well-defined element here. That's a useful index because actually this is very computable. It's unlike that group cohomology with Lie group is something totally insane. Differential cohomology is completely computable.
So can you give a sort of picture?
I'll show you. It does look very nice unless you know some technology, but I'll show you something. Yeah, so this is a modified anomaly index for Lie groups. And again, it has similar meaning. And there's even some non-zero some theorem that the non-zero anomaly index obstructs yet symmetric ground states. So well, that part of it is still a bit under construction. And that allows you to include the original LSM, for example, where the group is S3 things. So the point is that like this guy for SO3 is actually Z mod 2. And you have a representation of them with a half integral spin, actually it is non-zero, non-trivial value here. That you get LSM out of this general result. Now, by the way, while this might be difficult to explain, this is easy. What this labels is the class of smooth projective representation of genome. Smooth meaning, all your you think of it as a map to projective unitary group. When it's on its homomorphisms, then it's smooth in this as this map of Lie groups, from Lie group genome to the Lie group of projective unitary group. That's what this thing actually labels. That's why you see it's natural, because it's natural physically to consider smooth representations, smooth ray representations of it. In fact, if you look at some classic papers like from the 50s, like Bargman, that's what he assumed explicitly. Now, here is an important point that it was emphasized. In Q of T, there can be no mixed anomaly in translations and in internal symmetry. But in lattice models, there is. So lattice anomalies are not the same as Q of T anomalies. Another thing which should similar result, not similar, but also emphasizing this difference, is that actually, if you look at connected Lie groups, even though I can define this anomaly, it always vanishes for lattice systems. So, for example, so if your G is connected Lie group, then the anomaly always vanishes. So in particular, if your group is U1, so in this particular, if the group is connected, then actually this weird thing is actually just related to what's classifying space of the group one can show. This is what's labeled Chern-Simons couplings or all conductance. But there's no anomalies in lattice one-dimensional systems which represents them. Those trivial. So quantum field theories can have more general anomalies than any lattice systems can have. Well, any lattice system with finite dimensional onside Hilbert space. But another lattice systems can have some mixed anomalies which Q of T cannot have. They're just different. And finally, to answer the question, I'll try to at least roughly sketch what this is. Differentiable cohomology of degree 2 cohomology. We get lost in indices for a Lie group. So the point is that since G is a Lie group, and it's a manifold, and the problem is that the manifold can have non-trivial topology. So to deal with that, we're going to cover it with charts, with some nice charts. I'm not going to specify what nice means, it's a bit complicated. But basically, you just cover G by charts. And since in the cycle condition, you also have a function of two variables. You better choose some cover for G times G. And it's not the same. Of course, you can get cover for this by starting from cover from that, but that's not what you're going to do. Choose independent open cover of G times G. And also independent open cover for G times G, and so forth in principle. But for this degree 2, just need to cover this, and that in some nice way. Now also, so this U1 with index means that U1 is the cover, and I just an index with chart of the cover U. And U2 is the cover of independent with G times G, and so forth. And since I'm using the same font for different things because I ran out of economics. I have an infinite number of letters. So I'm gonna say it. So the labeling, these are like labeling sets for charts of the cover of G, charts of the cover of G, and so forth. Now also need double overlaps. So you're gonna be doing this like if you want IG, just overlap of charts I and J on G. And unfortunately double overlaps also of charts of G times G cover. Well, and also we don't triple overlaps of cover of G. Okay. Now what's a Tuka cycle? Or first of all, what's a Tuka chain? I don't have the time to explain what a Tuka cycle is actually. But anyway, what's a Tuka chain? Well, something which satisfies some equation, but what is this thing which satisfies the equation? Before it was a function of two group elements for a rho of GH. Now I'm going to be more data. First of all, there will be a function function on here. So for every chart on the cover of G times G, I'm going to have some function. We're going to have smooth functions with values in whatever condition group I have, say you want. But that's not all. Also, on overlaps of charts of the cover of G itself, I'm also going to have functions. Somehow the total degree is still 2, in the sense that, first of all, degree is made of two things. First of all, you take how many variables it depends on. Here, there's 2. And here you take, once you add the number of upper indices minus 1. So this guy adds 0 because 1 minus 0 is 1 minus 1 is 0. Here I have 1. So this guy is also sort of a 2, has degree 2 because it has single group element as a function. It has a single group element, but it also, this group element is in a pair of the overlap of two charts. Okay, and a Tuka cycle is a Tuka chain whose co-boundary vanishes. It's some linear condition on this pair of functions. And this linear map takes you from the space of these guys to some bigger space, some other space. Which space? Well, to a space of Fricka chains, right? So what is it? Well, something of degree 3. We're going to have functions on g times g times g on every single chart. We're going to have functional double levels of charts of the cover of g times g and right here, okay. Which is that, and here it's a triple overlap, so charts of g times g times g. Okay. That's smooth functions. And then there is some map from this data to this data. And a cycle is something where the map is 0, something which sends this guy to 0. And then there's a definition of co-boundary. Like it's really horrible, and I cannot write down to you the definition of this map without some technology. But there is a technology. It's called simplicial set technology. So, which allows you to concisely write this differential, which defines the cycles, and verify that it actually squares to 0. So the notion of a boundary and a cycle and stuff like that. So that's the thing. So we define this cohomology, and it's not very to degree 3 from the H3. Seems horrible, but actually, it's hard to define. It's very easy to compute, particular and maybe I won't discuss what I mean by locality preserving because it's not already out of time. So we have a rigorous definition of locality preserving, also this uniformly almost local thing. Basically, these are like quantum cell automata, but with tails. The where you map observable, which is local, something quite local but with tails. And if the tails decay faster than the power, that's the best situation when the resulting group kind of like a Lie group, interdimensional Lie group. So if you just have some tails, well, it doesn't the Lie group, but it's still nice big. Yeah, but there's no. I recommend this. All these notions were defined by the same authors. Well, not all of them. This one is by Ranar Walter. Very nice deep paper which explains, studies this general notion of locality preserving automorphism that shows, for example, that every one of them can be approximated by a sequence of quantum cell automata, which also equals to that decomposition to infinite product. It's a very natural notion.
Any thoughts on IRD or?
Well, it's possible, but computations in F and else with cycle condition verifying is pretty difficult. So one can even area, say for anomaly in 3D, which is still possible, but it should be possible to prove a result like similar to IAC L-string that some class in H4, if it's not rigorously, if it's non-zero, also differentiable case, it's non-zero that it's does not allow any symmetric and short entangled state. Of course, with gap, it's more complex. The gap state is something you don't have good control over the dimension, logically ordered, so you have saturated anomaly. Also, I should say that people who did study SPT phases usually pretend that they can deal with Lie group symmetries, but they don't. But this formalism of differentiable homology actually is completely falsifying that case. You're going to interpret whole conductance as something, as some group cohomology class. Actually, that's where it takes value in this group cohomology, differentiable group cohomology of U1. And one can define SPT index of U1 varying SPT phases, which takes values in this group cohomology and show that all conductance. Precisely the value of this index. So there's no similar. So there's no problem there. It sort of answers some questions which I will have. But why use measurable cycles? That's just not what.
Is there going to be some kind of spectrum structure on these locality preserving automorphisms?
Good question. I don't know. Yeah, it's maybe it's a matter of Kedai conjecture, but this locality preserving guys and uniform almost local because they're nice. Because this guy here just forms a pathological group. It's kind of difficult to work with. Local group is something very general. But this infinite dimensional V group, a lot more structures, so it's easy to work. Maybe they form a spectrum.
So these ones, could you say a bit more about these?
No, it just means that you act on a local, get something able to carry rapidly. And these are the Lie algebra, and the Lie algebra is something quasi-local. The Lie algebra is simply Hamiltonian with the interaction with decay faster than power. So that's a very nice. I don't know whether they form a spectrum. My guess is not, because to get the spectrum is a very tricky thing. You know, it's you need some stabilization, whatever. I don't know how to get that. Maybe we need to look at some, not a lattice system, but like lattice system embedded in some dimensional lattice. Then you get the spectrum. And you imagine acting on some d-dimensional sublattice and some lattice embedded in actually in infinite dimensional space. Then maybe then they get the spectrum.
So you mentioned that there's a difference between the lattice and QFT.
Yeah.
But maybe you can supplement the lattice with some sort of like bath or something. Because you were talking about how.
Well, I mean, if you like allow constraints on your lattice, like for example, people who studied the specific example, there's a paper by Metlitsky and someone else on Z2 fermionic SPT phases into dimensions. So there's a Z8 classification of those, and those. So there's a Z mod 8 valid invariance. When it's even, you can realize corresponding. When anomaly can be realized as lattice map. But when it's odd, it cannot be apparently. And Metlitsky and Squatter for the name show that it can be realized for constraint system, lattice system, some Gaussian constraints. So that's one option to get out of this. Another option is to use infinite dimensional Hilbert spaces on each side, like rotor systems. But it's not absolute, you know. This is all I'm saying is that you restrict to find on-site Hilbert space. Don't get all 15 hours expected.
I apologize if I'm misunderstanding something, but if I understand correctly, you said that on the lattice we can have basically a mixed anomaly between translations and on-site symmetry, while in QFT we don't have this because there is no mixed anomaly. But then what happens if we take if you look at the infrared behavior of the lattice, don't we expect that to be a QFT?
Yeah, well, I'm saying that as Chang and Cyber explained, you still see manifestation with lattice anomaly, typically, because you find some additional symmetry which you don't have on the lattice, like C2 symmetry, and then so that maybe ZN symmetry in general. And then you still see, you can detect anomaly, but it's not anomaly with translation. I mean, the continuous translation still, but there's no anomaly with those continuous.
So do we have a way from given this classification of lattice anomalies or corresponding anomaly?
Well, it's difficult because we're supposed to now compare a lattice with quantum field theory. It's kind of hard, so I don't know how to do that because they need to precisely define within the anomaly on the lattice. So I don't actually, like so the Chang and Cyber paper, they try to make a definition, but it's not very satisfactory because they work with things like partition functions, finite volume. They assume that they're non-zero everywhere as functional parameters. I don't know why one can assume that. It's not about phases of these partition functions. So that's not a very satisfactory way of dealing with it. But the function vanishes, well, what is its phase? It doesn't have a phase. So yeah, so there should be some other way to anyway, without having a good better understanding of QFT, it's difficult to compare them.
One way you can argue that you get this internal symmetry in the lattice is that you're doing some lattice size translation to the field. And you could do, you know, if you have fields, you could do some kind of derivative expansion of what you're doing. And, you know, the amount you're translating by is going to zero. So you're basically getting an internal symmetry at the end. But maybe
intuitively it's clear what it's a reasonable thing to assume.
But maybe what's actually happening is that you're adding other modes that are going the other way, like in your picture. translating the other direction. Is that possible?
Well,
Would that be a way of formulating this internal symmetry?
I don't see how to get the Z2. So still have by Z2 maybe like a swap symmetry with just to public or something.
Yeah, so if you add the extra chain and you have translation go the other way, then I think the circuit symmetry that you're talking about will exactly be the Z2.
No, but in general, I mean, for general ZN, if a cycle is like degree n, then I still only need to focus how big is ZN. Let's see.
Well, you're not guaranteed to. Let's get some ZN symmetry out of that. I see. Yeah. So when you do this, when you write these swaps, although it's a circuit, it still has Z rules. So
Right.
you have to know that thing.
Well, I mean, in
collapses,
general,
and it doesn't always.
you need to assume that something happens with the symmetry.
Yeah.
That some discrete, some factor, a quotient of your lattice system becomes a non-trivial symmetry.
It might not even be a quotient if you have, say, free fermions with k left and k right are irrational values. It'll just be some Z, and then you can't even say it's an anomaly because there's no anomaly where Z times is.
Yes, I don't know how to make this percent, but maybe there's some statement. If you assume something about the longer limit, maybe you can show that longer limit must have anomaly which matches that. So that would be a nice result. I'm not sure what to assume about PT.
Yeah. I would like to be able to say that this Z that kind of densely fills the axial U1 means that there's like some remnant of the kind of anomaly. Another question? No, let's think Anton again.